As a quick review, we're going to look at generating sets and bases. It's a good idea to follow along with the questions yourself and see if you can determine what the correct answer or answers are for these questions. Given a vector space V, what is a property or definition of a generating set or a spanning set if we have a collection of vectors? Think of all the things that would apply here. Okay, remember that generating is focused on building a set. And so that is about building with spans, and so this is going to be the answer we're looking for. The span of those vectors is equal to the vector space. Remember, span only applies to a set of vectors, so this logic here, the span of a vector space, isn't a thing. So only one characteristic here describes a generating or spanning set. Next up, how about a basis? If we have a basis which is considered to be a set of vectors v1 through vp for vector space V, what can we say about that? Pause for a second. Well, if you take a look at the arguments here, the set of vectors is linearly independent or dependent. Absolutely, we need the independence of this collection of vectors, and we also need it to be a generating set. So basis again is equal to a generating set plus a set that's linearly independent. Perfect. So a collection of vectors that has those two properties at the same time. For some quick examples, imagine categorizing each of the following vector sets by whether they are generating sets, linearly independent, and a basis for R2. So keeping it concrete, nice two-dimensional plane here. If we have the set 1, 0, and 1, 1, so that would be the vector here, 1, 0. And we have the vector 1, 1, so up at a 45-degree angle like so. Those are definitely, keep my parentheses consistent here, those are definitely linear independent. We have two vectors and they're not pointing in parallel directions. And is it a generating set for R2? Well, absolutely. Any point I can pick, I can get to there by some combination of a line parallel to the x-axis and then back along the 45-degree line. So absolutely, this is a generating set, and because we have yes plus yes, this is also a basis for R2. Now how about a contrast of 1, 0, so 1, 0, 0, 1, and 1, 1, each of those vectors? Well, by adding more vectors to that set, we can't lose coverage. Remember, generating sets about span, and adding more vectors is simply going to let us span either the same or more space. So we definitely have a generating set for R2, but we can see this is not linearly independent because 1, 1 is equal to 1, 0 plus 0, 1. So one of the vectors in the set is a linear combination of the other two, and that's one of the alternative definitions for linear dependence, is that one of the vectors is a linear combination of the others. And now we have a generating set, but it's not a set that's linearly independent, and so that is not going to be a basis. Finally, what about the vector set 1, 2, 1, 2, like so, and then the vectors 2, 4, let's do this in green, which you'll notice, hey, that's sort of a multiple of the first one. And what if we had the same but negative? Let's go down this way in blue. So we had -1, -2. So even though we have three vectors, there is a lot of redundancy in terms of their direction. And so what we get here is that this isn't even a generating set, because if I choose a point off to the side here, I can't get there by following linear combinations of these vectors. I can only move along this line here. Furthermore, we have several vectors that are parallel, and that's a quick test for not being linearly independent or are being linearly dependent, and definitely that is not a basis because we don't span the set and we don't have a set of linear independent vectors. So that's a nice exploration, at least in R2, of what those three characteristics of a set of vectors could mean and how we could classify them.